I'll just hold it up. Okay, yeah, so like Evan said, we're going to be reviewing everything that's going to be on the prelim topic-wise, and I'm going to be covering Gale Shapley and then part of greedy algorithms today. Should we wait for...
Yeah, is everyone...
There's like one seat over there and over here.
Yeah, squeeze in, guys. There's definitely enough room for more people to sit. Like second row, third row, fourth row. I see a lot of empty seats. Nice.
Okay. Wait, why do I feel like my microphone is so quiet?
Yeah, it's maybe just move it slightly higher, or you can take off the clip and just hold it.
Yeah, I think I'll just hold it. That's fine.
Yeah, you can sit on the floor, or you can sit in the hallway. I mean, yeah, either works. Yeah, this is insane. Last semester had nowhere near this many people. Also, the course like doubled in size, right? So feel free to sit on the floor and find some space, but also please keep like the aisles kind of clear, you know, just in case of any emergencies, so we don't get trampled. But yeah.
Okay. Okay, we're gonna get started. So yeah, let's get started with stable matching. So wait a minute. Can you reload the slides? Sorry, I had a slide right before this. Okay. I've also compiled some just general tips for the prelim in general. So the first thing that I recommend is just to try to get as much partial credit as possible. Even if you don't exactly know how to prove the DP solution, it's going to be really helpful to just write down what the recurrence relation is, or at least give it a try. Getting partial credit is going to really help you on these exams. Understanding the problem statement is also very important. So what is the problem asking you to output? For example, in DP solutions, is it asking you to output maybe the optimal number, or is it asking you to actually output the pairs or the organizations in order to get that optimal number? Understanding the inputs are very important as well to see what kind of information you have at the start. Considering the pre and post processing in your runtime analysis, I've seen a lot of homework so far is people are kind of only considering the bulk of the algorithm for the runtime analysis and not considering what it takes in order to pre-process the inputs to get it to that point where you can actually run the algorithm. Familiarizing yourself with the algorithms you've seen before, and also in the Kleinberg and Tardis textbook. We're going to go over some of them today, but I also recommend just familiarizing yourself with them. They might give you some intuition on what kind of greedy choices to make, or if you can reduce it to something else, or you know, like what kind of subproblems you might use for a DP solution. Reviewing homework solutions and understanding why you got points off. If you want to go to office hours and ask a TA, you know, to look over your homework and understand why you got those points off, that's going to be super helpful. And then finally, prioritizing. Oh wait, there's actually two more. One more is prioritizing active learning. Writing your own proofs is always going to be better than just looking at the textbook and reading it and being like, okay, I got it, because a lot of times you're kind of just reading it and then you're convincing yourself you understand it when you really don't. And then the last thing is just not assuming that knowing the answer is enough. If you know the algorithm and you look at the answer key and you're like, okay, I got the algorithm, that's not really enough. You need to know how to prove that. So I'd always recommend writing the entire proof when you are practicing for these kinds of exams. Okay, let's get started into stable matching now. Okay, so the stable matching problem, you guys should be familiar with it. It's a set of n men and n women, so they're equal to each other. The number of men and women are equal to each other. The men are the ones proposing usually, and each person has a preference list for the other gender. Yeah, we want to find a matching that's stable. What a stable matching means is that it's perfect and there's no instability, and we've labeled an instability as an instance where there are two pairings, but each person prefers the person in the other pairing to the person that they're currently matched with. Does everyone understand this problem statement for Gale Shapley? All right. So let's practice it then. So say we're given these men and these women with the preference lists up here, and the colorings indicate the people that they're matched with. Would this matching be stable?
Don't all shout at once.
Oh, yeah.
M1 prefers W2 to its current match, and W2 prefers M1 to its current match.
Yep. This would not be stable. Right, so you can see that M1 and W2 both prefer each other over the person that they're currently matched with. So this would not be stable. Okay, and then we get to the Gale-Shapley algorithm, which is going to produce these stable matchings that we want. The way Gale-Shapley works is that every man proposes starting at the top of their preference list. If the woman isn't already matched to another man, she's going to say yes to that man's proposal. If she is already matched to a man, she'll only say yes if she does prefer the man who's proposing over the man that she's currently matched with. You keep running this algorithm until every man has proposed to women, and then at the end you're going to get a perfect stable matching. You can also look at the textbook that gives you a little bit more detail on that. And then question here, is it possible that there are still unmatched men or women after this algorithm finishes, assuming that there are equal number of men and women? No. Yeah, no, it is not possible. Okay, properties of Gale-Shapley. It always returns a perfect stable matching. If the same people propose, then the stable matching is always going to be the same matching. That's also really important. The proposers are always matched to their best valid match, but their matches are always going to get worse as the algorithm progresses. So this can be kind of confusing. What that basically means is that out of all of their valid matches, they're going to get matched their best one, but as it progresses, right, they're going to have to go down their preference lists in order to find their best valid match. So their matches are going to get worse over time, whereas the respondents are always going to get matched with their worst valid match, but their matches are going to get better as the algorithm progresses, right? Because they're only going to say yes to men who they prefer over their current match. Okay, does that make sense to everybody?
There was a net question about this earlier, and so I do want to make sure that that's like crystal clear. Like the difference between best valid match and also like why it is the case that hospitals get worse, right? Is everyone clear on the definition of valid match? And what is a valid match? One that won't induce an instability in the matching. Right? So like just because a hospital prefers a resident on its preference list more than one that gets matched to, if that matching creates an instability for some other matching, then it's not valid. Right?
Awesome. Okay, and then let's do some true false for Gale-Shapley as well, just to make sure everyone understands it. The first one, the outcome of the stable matching problem when men propose to women is the same as the output when women propose to men. True or false? False. Consider an instance of the stable matching problem in which the first choices of all men are distinct. Let these top choices define a matching M. Gale-Shapley will necessarily return this matching on all instances with this property. True or false? True. Yep. Oh, okay. You didn't see that. Consider an instance of the stable matching problem in which the first choices of all women are distinct. Let these top choices divide a matching M. Gale-Shapley will necessarily return the matching on all instances with this property. True or false? False, right? If a woman receives proposals from at least K plus 1 M, K plus 1 men, then she is not matched to one of her K lowest priority men. Conversely, if a woman is not matched to one of her K lowest priority men, then she has already received proposals from at least K plus 1 men. True or false? Yep. Awesome. Nice. Okay, before we move on, anyone have questions, residual questions about Gale-Shapley or anything we just went over in terms of stable matching? Yep.
What's the intuition behind like the men matches get worse and worse, but it's also like not optimal?
Yeah. Okay, so let's go back to the proposers. It's not necessarily the men. It's just going to be like you could be like hospitals, whatever. But yeah, the proposers are always going to get matched their best valid match, but it's going to get worse over time. What that means is like, we start off at the top of their preference list, right? But there's always a chance that that match could be an instability, which would mean that that match is not a valid match. So as the algorithm progresses, although their matches are going to get worse, it's always going to be the best valid match because as it gets worse and worse, those are going to be the ones that are invalid, right? The ones that they're discarding, which means that by the time they get to their first like actually valid match, that's going to be the best possible one for them. But I know it can be kind of counterintuitive because their matches are getting worse over time. But you can kind of think of it as like all of the ones that are better are not valid. Does that make sense?
Yeah.
Yep.
On the exam, if it asks for a counterexample, is like drawing a matching enough, or do we have to like explain it with pros?
Yeah, you could just draw an example or give an example. That's enough.
Usually your examples are inputs to Gale Shapley's and specify like the preference lists. And even then, I don't think you would need to specify the exact matching if they're this time. But it's helpful to specify matching too.
How formal does the notation need to be? Like any of my responses for prelim?
Like your proofs or
Like for this or just in general?
Or like notation wise, like for example, putting them right, like I don't know, like how detailed does it need to be?
so your proofs should always be as formal as possible. I'm not sure what you mean by like notation.
I mean, like a big part of this class is understanding how to take a problem that is specified in plain English and introduce enough notation to solve it, right? And so in that sense, like you're held to the same standard as you are on the homework, right? Like you should be able to introduce enough mathematical notation that you can formally specify an algorithm and rigorously prove it using the techniques that you know, right? How much is enough kind of depends on the problem, right? Like some problems are very easy to specify with very little notation. Some problems you need quite a bit of notation to specify exactly how you're going to do things. Does that kind of make sense?
And one thing that I did see a lot in the homeworks is people just writing statements without proving it though. It does need to be, if you're gonna claim something is true, unless it's like extremely, or what's the term for that? Unless it's trivial, yeah, sorry. Unless it's trivial, then you do need to just say something like, oh, an instability is equal to whatever that question on homework 1 was, I forgot. Any other questions about Gale Shapley? Yep.
Should we know how to prove the last two properties?
So you can kind of take these, you already know that these are true because they've been proved in the Kleinberg and Tardos textbook in Gale Shapley. So you can take this as just as a property of Gale Shapley. Yep. Yes. Yep.
Yeah, just to add on to that, you're never going to be asked to like reprove something you've already proven in class. Similarly, you will not be asked on this prelim to like regurgitate an algorithm that you already learned in class, right? So the goal is to like take inspiration from the proofs and from the algorithms that you've seen so far in all of the lectures, but you will not be asked to like prove this property of Gale Shapley, right? That's kind of a memorization question, not an actual algorithm question.
So like if we show that like something can be reduced to an knapsack problem, like we just write, okay, this is like all correct now for like knapsack.
If your reduction is correct, yeah. If you correctly prove that it can be reduced to knapsack. Yes.
Can you explain why is it always like the worst valid match for the respondents? Like, doesn't it depend on the like who proposes to them, kind of? Like who the respondents get?
Yeah. So when we say the respondents are matched to their worst valid match, it's kind of like the same thing as like the proposers getting matched to their best valid match. Like it's always possible that like initially, or I guess so their matches are getting better as the algorithm progresses, but they're still only going to get matched to I don't know how to describe it on the other way around. They're only going to get matched to like their worst match that won't cause an instability. So like there's no case in which they're going to get the best valid match, like the highest, maybe like the highest on their preference list, because this is like a proposer optimal algorithm, if that makes sense. Yep. Oh yeah, yeah. I can repeat them from now on. So, I mean, some of the ones that people asked is how rigorous the notation had to be. And then if something's in the textbook, you can assume that it's true and we won't ever ask you to prove stuff that we've already proven in class. But yes, I'll start doing that from now on. Thank you. Any other questions? Okay, let's move on. So greedy algorithms. So far, you guys have seen a few greedy algorithms like the interval scheduling problem, scheduling to minimize late, Huffman encoding, and minimum spanning trees. So okay. And then these are some proof techniques that we've used in the past to prove greedy algorithms. So greedy stays ahead is basically it's showing that the algorithm is always going to be as good as the optimal algorithm by showing that at every step it's going to be at least as optimal as the optimal solution. And then exchange arguments is showing that any optimal solution can be swapped with our greedy solution and still retain its optimality. We'll go into this a little bit more in detail later.
I don't recall if Ishan covered minimax at all, but if you've never heard that word before, just ignore it. Yeah.
All right, so interval scheduling. So here is kind of just the setup for the interval scheduling problem, which is given a set of n requests, as well as start time and finish times for any request I, schedule as many requests as possible. So the optimal greedy rule that we've used, and we've covered this before, is earliest finish time. Does anybody know the intuition behind why we've chosen that greedy choice for this problem?
So you go for as much as possible.
Yeah, so you're basically trying to, whenever something is done, you want to start as soon as possible on the next thing. So that is the greedy choice for interval scheduling. Right, so this is the intuitive explanation for it. So every greedy choice kind of does have an intuitive explanation, and there are only so many greedy choices you can make, right? You could say earliest start time, shortest length of the interval. You can choose based on the least amount of conflicts with other intervals, but there is like a limited set of greedy choices you can make, and you can always kind of just choose and then see if you can find a counterexample if you're really, really lost. This is the interval scheduling algorithm, which is basically we sort all the requests by their earliest finish time. We pick the one with the earliest finish time, delete every other request that conflicts with that one, and then continue on. Okay? Does anyone have questions about this greedy algorithm? Yep.
So we think it's accurate to like start with the latest starting point. That's the same thing, right?
Yeah.
They don't produce the same solution.
Alright.
They produce the same.
Yeah, you can prove that those proofs are very similar: earliest finish and latest start. Okay, so when we're doing a proof for interval scheduling, we want to kind of go through the steps of what a greedy stays ahead proof might look like. So what are we trying to prove for this problem? We're trying to prove that the size or the amount of intervals that we can schedule using our greedy algorithm is going to be the same as the amount of intervals that we can schedule using some kind of optimal solution that's kind of arbitrary right now. And then how are we going to prove that? We need to prove that our greedy solution, which is picking the earliest finish time, is always going to stay ahead of the optimal solution, and we're going to go into that in a little bit more detail. But we do need to define what it means to stay ahead in general. Does anyone have any ideas about what it might mean to stay ahead of the optimal solution in this case? Okay, that's okay. We'll go over it in like a second. So, and we're going to do this using induction. Okay, so for the interval scheduling problem, we've defined staying ahead of the optimal solution to be if we have ik and jk, those are both the kth interval in the greedy algorithm set. So ik is the kth interval in the greedy algorithm set, and jk is the kth interval in the optimal set of requests. We want to show that the finish time of the kth interval in our greedy algorithm is less than or equal to the finish time for the jkth interval in the greedy solution set for all k. Okay, so that's what we've defined as staying ahead, is that ours is going to finish before the kth interval in our solution is always going to finish before the kth interval in the optimal solution. That's what we've defined as staying ahead. Does that make sense to everybody? Awesome. And then we're going to prove this using induction.
Is everyone clear on the idea that like when we're defining a metric by which a greedy algorithm stays ahead, it is not the same thing as saying it like is better than the optimal solution, right? So this does not immediately mean we've proven the correctness of our algorithm. After we've done our inductive proof to prove this fact, right, that does not imply the optimality of the greedy solution. You then need to take one more extra leap of logic to show why your greedy stays ahead claim implies the optimality of your greedy algorithm. Right? So there's like two separate proofs that you kind of need to do for a greedy stays ahead algorithm.
Yeah, and we'll show an example for that in a second as well, if you're a little confused. Okay, this is kind of non sequitur, but tips for designing greedy algorithms. So the first thing we want to do is make sure it's not actually a DP solution. So I talked about this a little bit, but there are only a finite amount of greedy choices you can make for a given algorithm. If none of those work and you can find counterexamples to every greedy choice, then it's probably not a greedy algorithm, and then you should probably use DP. And then what are some metrics that can be used to fuel the greedy rule? Like I said, what's that finite set of greedy choices you can make? Yeah, earliest deadline, smallest interval, etc. And then does it look similar to any of the problems that you've encountered this semester? So Huffman encoding, interval scheduling, MSTs, anything like that. Maybe you can use a reduction or use a greedy choice that's kind of similar to those algorithms. And then finally, proofs, exchange and greedy stays ahead. These slides are going to be posted, and I would recommend looking over these sections in the textbook if you're confused. Yep.
Wait, like, how do you like identify if it's like DP or greedy? Like, is there some like?
Yeah. We'll talk about that later. Okay. Yes, so let's go back to the problem that we were just going through, which is our interval scheduling, and we're going to talk about the guidelines for greedy stays ahead in this case. So we've defined the solution generated by our algorithm as well as just an arbitrary optimal solution. So for example, if our solution is the set of A and our optimal solution is the set of O. We define the metric in which our algorithm is going to stay ahead, which we defined as for the kth interval in our solution as well as the optimal solution, our solution is going to finish before the kth interval in the optimal solution. That's our definition of staying ahead. Yeah, this metric should also mention the way that we're ordering the elements of O, and then use induction to prove that greedy stays ahead. Okay, so for the problem that we just did, the base case would be that obviously for when k is equal to 1, so the first interval, our finish time is going to at least be earlier or equal to the finish time of the first interval in the optimal solution. And why is that true? Our base case.
That's how we design the algorithm first, or fix the interval finishes.
Yeah, exactly. So we've literally defined our algorithm to always choose the first earliest finish time. So of course, the first interval, our finish time is going to be before or at least equal to the first interval of the optimal solution. Does that make sense to everybody? The base case? Okay, and then the inductive step is where you're going to actually prove that greedy stays ahead. So you're going to assume for all k interval or k minus 1 intervals, you can do strong induction or weak induction. I guess for this one we can use weak induction. So if we assume that our statement at least holds for the k minus 1 interval, then we can prove that for any k greater than 1, we can assume that our inductive hypothesis holds for that. And I don't know if there are some examples, or I don't think we kind of go into depth because this has been gone over in the textbook. If you want more, the entire proof for this one, it's in the textbook. But that's kind of how we go through using induction to prove the greedy stays ahead, is proving that it works for all k minus 1, or it works for at least k minus 1, and then proving that that implies it works for k. Yep.
So with the ordering of the elements of O, how do you determine how those elements are ordered?
So how do you determine that the elements are ordered for the optimal solution?
For instance, like the metric should also mention the way you are ordering the elements of O. How do we like?
I think they just mean like if we're creating an optimal O, like O1, O2, they just mean that they want us to specify like what O1 and O2 is, because it's not going to be like interval 1 or interval 2. In this case, O1 and O2 is going to be the first scheduled interval and the second scheduled interval. So it's just we don't know what the optimal solution is because it's arbitrary. So it just wants us to specify like what the elements of O are. Does that make sense? Okay. Yeah, and then finally what Evan was talking about is that's not enough. Once you've proved that our greedy stays ahead, it doesn't really mean anything until we prove that the greedy stays ahead. Greedy staying ahead, an arbitrary optimal solution implies that our solution is also optimal. It should usually follow pretty naturally if you've chosen a good stays ahead metric. In this case, our stays ahead metric, it's going to follow very naturally that the set of A and O are the set is a set of A is at least as optimal as O. Okay, but that this last step is also very important. You can't just stop at the induction of the staying ahead and then assume that that's optimal. Okay, does that make sense to everybody? We're also just going to go through a problem for greedy stays ahead as well. Okay. Yes. So this is kind of a long problem. Yeah, just look at it. I mean, the algorithm is already on here. Yeah. But think about what it would mean to stay ahead for this problem. We'll give you like 10 minutes.
talk to each other as well and try to think through this, and then we'll also just walk around and kind of help and see what people did. No, I don't think we can walk around.
看到第三段的时候就惊了，为什么要这么干？然后可能就知道哦，那没事。但是他说是你要会看到我的。
That's good. Yeah, more boxing.
Already saved.
That's the slight, yeah.
That's what they're saying. Right? How was the line? How would that help? They're saying like 5 days. Yeah. Why do you have services? Oh, so what they're doing right now is that they're taking everything at the moment that like process. How much coming down? Yeah. Yeah. Yeah, so how did we go with it?
So what they're saying is,
That is a
oh, we're trying to show like it worked.
Kind of show that. Okay. So like if you unlock the side and you put it like other that's violation here. Yeah.
Oh, the metric?
Okay, let's go over the problem now. So Does anybody have any ideas as to what metric we could use for greedy stays ahead?
Perhaps you could say like for each, like for I, where I is the I truck in your solution, and J is the J, and I is also the like the I truck in the optimal solution, and then from A1 to AI, which is the truck in your solution, and O1 to OI, which is the truck in the optimal, that the weight in your greedy is like always greater than or equal to the weight in your optimal.
Okay, so I think I heard most of that, which is from, so you're basically saying like for K trucks in the R solution and the optimal solution, the weight of our solution is at least as or is greater than or equal to the weight of the optimal solution. Okay, that's one metric we could use to prove that it stays ahead. Does anyone have any other ideas?
The number of trucks for our solution is less than or equal to the number of trucks for the optimal solution of the weight pi.
Okay. Yeah. So that's another one where up to some weight I, the number of trucks in our solution and the optimal solution, the number of trucks in our solution is at least or at most the number of trucks in the optimal solution. Okay. Yep.
So given the K of the truck, the last box that it carries is, so if it carries the last box, it carries box J, and that's greater than the K of the truck of the last box that it carries.
Like the weight of the box?
No,
Or
like
the number?
of the box.
Okay.
The last box that you got in our solution is bigger than the last box of the optimal solution.
Oh, okay. So one other is if you number the boxes from 1 to n, the kth box is always going to be, for our solution given a truck, is always going to be further in the 1 to n than in the optimal solution. Okay. Yep.
The 10th box has to be sent before the 11th box, so we don't really care about the weight, right? That's a bit.
Well, there's a maximum amount of weight that they're allowed per truck. Well, I think yeah, we're just brainstorming right now. Okay, so he was asking basically why does the weight of the box matter? Okay, but those are all great suggestions. So this is the suggestion that we went, or this is the metric that we went to for greedy staying ahead. So A is going to be the total number of trucks that our greedy solution uses, and O is going to be the total number of trucks that the optimal solution uses. That's what we're going to use in order to define greedy and optimal. And then the metric in which the greedy solution stays ahead. So for the first K trucks, our greedy solution packs boxes B1 to BM, and then the optimal solution packs boxes B1 to BN. So it's also important to note that this ordering is sequential, right? Because it matters that we ship boxes that come first before boxes that come later. That was mentioned in the problem statement. Right, so if box BI comes before box BJ, then BI should be shipped out first. Okay. Yeah, and so our metric is that M is always going to be greater than or equal to N. So that basically means like the number of boxes that we pack at truck K in our greedy solution is always going to be greater than or equal to N, which is the number of boxes that we pack in truck K up to truck K for the optimal solution. Okay, I think someone mentioned something like that, or something very similar at least. So that was good intuition. Yeah, so that basically means that for a set number of trucks K, our greedy solution is going to pack at least as many boxes as the optimal, which is M is greater than or equal to N. Does that make sense to everybody? That metric for staying ahead?
I think the comment that the weights aren't necessarily what defines the greedy metric was a good observation, right? Because if we go back to the problem statement, right, boxes have to be shipped.
Boxes have to be shipped in the order in which they arrive, right? So your only option to choose like a different greedy rule would be to like postpone packing some boxes in a truck and sending it off before it reaches capacity, right? So intuitively that makes no sense as an algorithm, right? Any decision which you make where you don't just pack as many boxes as you can into the truck and then send it off doesn't really make a whole lot of sense because you have to send them in the order in which they arrive.
Yep.
why, we have to note that it is at least better than the optimal, because you kind of know by intuition that m is gonna equal to n. Okay? Like why do you have to like particularly note that n is greater or equal to n?
Yeah, okay, so the question is asking why we have to prove that our greedy solution is at least as good as the optimal solution, when intuitively, right, if we think about this problem, we know that our greedy solution is going to be equal to like the optimal solution. I think that's kind of like the question. So again, I feel like the optimal solution, we don't really know anything about it technically. And yes, this problem is intuitive, but we're just kind of giving this as an example for when an algorithm might not be intuitive. And because we don't know anything about the optimal solution, we have to do greater than or equal to, because we can't just really use intuition. And then you'll see it also makes it easier once we start getting into the inductive part of this, that making this greater than or equal to is going to provide an upper bound. Actually, yeah, no, a lower bound on our inductive step, which is going to be really helpful. We'll get to it in a second. Yep.
But just to make sure, it is still appropriate to say that like we can say that like our metric is that given a certain amount of boxes, we have the minimum amount of trucks. Would that be like logically equivalent?
Wait, what for the metric? The metric for greedy staying ahead?
Or like a given number of boxes, we have the minimum.
Okay, so if we have boxes 1 to m, we're trying to prove that the number of trucks that our greedy algorithm uses is at least, or is at most, the number of trucks that the optimal solution uses.
That's what you're trying to prove though, right? Like that is the entire algorithm. You want to prove that we don't use any more trucks. So you can't really use that as a reason. Okay, right? That kind of makes sense. Yeah.
Okay, so this is what our solution is going to look like. So the inductive part for k is equal to 1. So if you remember, what k represents is just going to be the number of trucks at this given point. So base case follows pretty simply. Our greedy algorithm is going to pack as many boxes as possible into the first truck. So m is going to be greater than or equal to n. So the number of boxes in our greedy solution is going to be at least as much as the box, or yeah, at least as much as the boxes in the optimal solution. Okay, that's our base case. And now our inductive hypothesis, we're saying that assume for k minus 1 trucks, the greedy solution holds, right? Yeah. Our greedy solution fits m boxes and the optimal solution fits n boxes, and m is greater than or equal to n. So we're just saying we're using strong induction to prove that for up to k minus 1 trucks, this m is greater than or equal to n statement is true. Okay. And now for the inductive step, we need to prove that if that is true for k minus 1 trucks, that implies that it's true for k trucks. So yeah, so our greedy solution, we'll say it fits m prime boxes, and our optimal solution fits n prime boxes. We want to prove that n prime is greater than n prime. So this, I don't really want to just read the solution out to you, but basically, if we know that m is greater than or equal to n using the inductive hypothesis for k minus 1, we can create a lower bound on it. So we can say that n prime minus n plus 1 is greater than or equal to n prime minus m plus 1. We know m is greater than or equal to n, which kind of leads to m prime being greater than or equal to n prime. Okay, so like I kind of said before, using the greater than or equal to inequality as part of our greedy stays ahead metric is really useful once we get to the inductive step, because we know that for k minus 1, m is greater than or equal to n. So adding one more truck onto it, we can kind of use that the inductive step in order to help us there. So you can also read the slide that kind of gives a little bit more insight, but that should be relatively intuitive. You guys have taken, or you guys know about induction, you know how that works. And then we need to prove the last part again that we've emphasized is that's not enough. We need to prove that the greedy staying ahead of an optimal solution implies that our algorithm is optimal. Yeah, so if the total number of trucks that our greedy solution uses to pack all boxes is n trucks, our proof shows that we pack at least as many boxes as the optimal solution. If we pack all the boxes, then that implies that n is the smallest number of trucks needed to pack all the boxes. Okay, so those like 2 sentences are what kind of finishes up the proof once you prove that our greedy solution stays ahead of an optimal solution using induction. Does anyone have any questions about how we structure these proofs, or kind of how we went about solving this problem using greedy stays ahead? Yep. Yeah. So basically, if we know that our greedy solution at the k-1 truck packed m boxes, then that ours is gonna pack, our greedy solution at this step is gonna pack m+1 up to n prime boxes and potentially more. So that's kind of what we're trying to prove. And the way that we prove that is we kind of just use the fact that, where is this? N prime minus n+1 and n prime minus n+1. So these two, n+1 and n+1, right? We're using the m is greater than or equal to n from the last inductive step, right? And we know that m is greater than or equal to n at the last inductive step. So when we add it to this n prime, which is the number of boxes that the optimal solution packs at the kth truck, when we are adding those values, we know that m is going to be greater than or equal to n. So that this solution kind of implies that n prime is going to be greater than n prime. And then so that's what we mean when we're creating a lower bound on m prime. Does that make sense?
I mean, remember, like, we're inducting on the number of trucks, right? So like the kth truck, which boxes does that pack? If we're saying n prime is like the total number of boxes for the kth truck using the greedy or the optimal, whichever one it is, right? Then you pack from n+1 to n prime, right? And then similarly for the other solution, you pack from m+1 to m prime, right? And you already know that m is greater than or equal to n, and so you have a relationship between m+1 and m+1 if you have a relationship between m and n. Does that make sense?
Okay, that's it for greedy solution or greedy. Oh no, there's more. Right, exchange algorithms. Okay, so exchange algorithms. This is kind of a general guideline of how it should go. You guys have done exchange algorithms in your past, or exchange arguments, sorry, in your past homeworks. So the first thing you need to do is you need to compare, again, like greedy stays ahead, your greedy algorithm to some arbitrary optimal solution. We'll call it O. Yeah, okay. So let's say A is going to be the matchings that our algorithm chooses, and O is another set of arbitrary matchings. And we're going to assume that that's optimal. We don't really know much about it. Then we need to choose some ways that our greedy solution A differs from O. So that could be a number of ways. That could be maybe there's a pairing in A that isn't in O. There's a pairing in O that isn't in A. There's an inversion, which means that the pairings in O and A are matched to different people. So you need to find every way that the greedy solution, your solution A, and the optimal solution O differs, and then prove that if you swap the option with your greedy solution, it doesn't become any less optimal. So we're basically trying to make the optimal solution, this arbitrary optimal solution O, more like our greedy solution A, and we're proving that that doesn't reduce its optimality by anything. Okay, so when that's where the name exchange argument is from. We're exchanging elements in O to make it more and more similar to our solution A. And what that's eventually going to prove is that when we make an optimal solution more like our greedy solution, that doesn't make it any less optimal, which implies that our greedy solution is optimal. That's kind of like the baseline for an exchange argument. The order is important. You want to make the optimal solution O more similar to A. You're not trying to make your greedy solution look like the optimal solution. You're trying to prove that your greedy solution is optimal. Yeah, so by doing these swaps, anytime we find differences, like I mentioned, there's a number of differences between O and A. If we swap it every time we find a difference, we're making O more like A, proving that there's no loss of optimality, which implies that our solution A is equally as optimal. Does that make sense? Does exchange argument make sense? You guys saw that on homework 2, I believe. You had to find all of the ways that your pairings differ from the optimal solution and then prove that they were the same level of optimality. You could prove that by like cardinality of the two sets. Does that make sense? Exchange argument? I also put, so if you look at Kleinberg and Tardos, page 129, there's a really good exchange argument there as well. Yep.
You always have to prove that they're, you always start by saying like they match up to some iteration, right? Like that's
Like, do you always need to prove that like they agree with each other on?
Yeah.
That's what we do in this course.
Okay. Yeah. So yeah, you can prove that they agree with each other up to some I. And that's where you find the first difference, and then you have to make the swap and prove that there's no loss of optimality. Yep.
sorry, you need to prove that the same unto some I? Can we just say we take the first difference?
You assume that they're the same up to an I, and then that's where the difference comes from. Yep.
Just to clarify on the swapping, like we're not actually swapping one item with O for A, like we're just changing the item. So otherwise you would change and then it would
Yeah, so we're swapping what's in A to B and O. So basically, like if O has a pairing I, J, and A has a pairing J, K, we're putting J, K into O and proving that that doesn't lose optimality in O.
we don't put the solution of O into A, like
No.
it's not an exchange, it's just updating O.
Oh, yeah, no, I guess in that way it's not an exchange. It's not like a fair exchange. We're just exchanging one way to O.
How do you know where to do goody space ahead versus strange?
So you don't. I guess you can prove it either way, but one's going to be significantly easier in most cases. Let me try to think.
I think
If you have tips.
Yeah, I think a general intuition for me that helps is greedy stays ahead is usually used to prove something about like cardinalities of sets, right? And so like optimal subset of a set of items. So interval scheduling, we want to maximize the subset of intervals that we can get, right? That basically ensures non-overlapping intervals. Exchange argument, normally you need to take everything in the set and you're trying to prove an optimality of the ordering of those items, right? And so by making, O more like A, we don't change the number of items in the set, but the ordering is more optimal, right? Now there are exceptions to that, like the minimum spanning tree problem uses an exchange argument, and we'll talk about MSTs in a second. And even though that uses an exchange argument, we're taking an optimal subset, right? So there are still like some exceptions, but generally that guideline helps, I think.
Yeah, I also think it might be complicated to find a stays ahead metric for an exchange argument problem. So if we think about your homework problem from homework 2, it's going to be really tough to find some sort of metric that proves that your solution stays ahead of an optimal solution rather than using an exchange argument. So if you can't find a metric, it might be exchange.
All right.
All right, so we're going to talk about MSTs. I think this kind of deserves its own section just because they're pretty important. And I guess I'll just preface by saying, so all of the named algorithms in this course, like you're expected to know better than maybe the non-named algorithms. And so the ones that you've seen, also you can take a look at the syllabus and that kind of gives you a hint as to like which algorithms are the most important to know. So the ones that you've covered so far are stable matching, so Gale-Shapley's algorithm, minimum spanning tree algorithms, particularly Kruskal's and Prim's, and Bellman-Ford for shortest path using dynamic programming. The last one is Ford-Fulkerson, and you'll cover that when you get to network flows later in the course. So those 3 algorithms you should know like the back of your hand. Like you should be able to run those on any instance of the problem. Kind of an upfront. Okay, so what is a minimum spanning tree problem? We have an undirected graph G, and we denote that as a set of vertices and edges VE, and we want to find a subset of the edges such that all of the nodes in our graph are still connected. So we can get from any node to any other node in the graph, but there's no cycles, right? So it's a tree and not it's a tree, but not a graph anymore, even though trees are still graphs yet. And the total cost of the edges in T is as small as possible, right? So we assume that each edge E in E has some cost associated with it. We want to minimize the total cost that we have that still spans the tree, right? Yeah. Does anyone intuitively understand like why such a connected component, I guess, wouldn't have any cycles? Right? Yeah?
Remove an edge from a cycle, it's still connected.
Right, you can still get there, right? So assuming positive weights on all of our edges, even if you remove an edge from a cycle, you can still get to all of the edges, so it does not minimize your weight to add a cycle. Question?
When you say that like it's a tree, you mean that like it can be organized as a tree, not that it's like the actual path ends up like being a tree, right?
So I mean, I guess it depends on like how you're defining tree. What I define by tree is just a graph with no cycles.
Okay.
Yeah. Okay. So the first algorithm that we covered was Kruskal's algorithm, which is fairly simple. We just sort all of the edges in increasing order of cost. We take the cheapest edges. No. Yes. We take the cheapest edge so long as it doesn't create a cycle, and then just add that to our set, right? And we prove the optimality of this using an exchange argument in class. And this runs in k log v time. And specifically, if you're going to get it to run in k log, or not k log v, e log v time. If you're going to get it to run in this time, you need to use union find. But we didn't have you implement it in this iteration of the course, so you don't need to know too much about that. You're allowed to just cite that the runtime of cross schools is E log V. Yeah.
Previous slide, you mentioned that they had positive edge weights.
Yeah.
Would it work if they were negative?
So there's variations of minimum spanning tree problems where you can allow minimum cost edges, but then it introduces some complexities into the problem that we kind of keep outside of the scope of this course. Yeah. Yeah.
On the homework, says that the runtime is E plus V log V.
So on the homework, the runtime was E plus V. You said E plus V log V, log V, right? Because we did a reduction and changed the cardinality of V, right? Like we added more edges and more nodes. So then the runtime, in terms of the original input, G equals V is different, right? Yeah.
So that we can just find cycles.
We can find cycles.
Like, because you said, because like for example, in the
Oh, like add it so long as it doesn't create a cycle.
like
yeah.
because in the practice exam, it just said find the cycle without really saying how to find the cycle. So can we assume that like, so since we didn't need to know the algorithm of finding the cycle, we can just say find the cycle.
Yeah, I mean cycle finding is pretty easy. So yeah, you can assume that you can just do it in a step of your algorithm. If there's like an instance of cycle finding that's more complex, then you would want to like specify exactly how to do it and the runtimes of it. But in a case like this, like to check and see if an edge that we add creates a cycle is really easy by just iterating through all the edges we've already chosen, right? So that's not difficult for us to do.
I think this is an operation in the union find data structure where you see whether these 2 points are in the same component, and you can check that in O of log n time depending on how you.
Okay, so Prim's algorithm works a little bit differently. All we do is we choose some root node, and it can be any node, and then we just try to grow the tree out from the root node, right? So we select the minimum cost edge that is basically outward from the connected component that we're currently growing, and then stop once we've connected all of the nodes in the graph, right? And does it intuitively make sense why it's the case that we can choose any root node to start and why it doesn't matter? Yeah. Right, all the nodes have to be in the tree anyway. It doesn't matter where we start from, we'll still get the same tree, right? So I guess a food for thought question, right? We assumed distinct positive edge weights. What if they weren't distinct? How could we manage that? Yeah?
Add slight perturbations.
Yes. Exactly, right? Because if they're not distinct, then that means there's probably multiple minimum spanning trees at work. So we can just slightly perturb the edges, add some epsilon to the ones that are the same, and it makes them distinct, and then we run the same algorithm, and we get an equally valid minimum spanning tree either way. Okay.
Wait, epsilon just feel like some arbitrary value.
Yeah, I mean, hopefully super, super small as to not corrupt the current ordering with respect to the rest of the edges of the graph.
So think about epsilon for every single edge that's the same.
Yes. Yeah. And you would tweak them differently for like different edges that are the same, right? So if I have 2 edges that are 2 and 2 edges that are 1, I could have like the same epsilon, right?
Why do you need the epsilon part? Why do they have to be distinct?
Why do they have to be distinct? Because your algorithm doesn't have like a tie-breaking metric built in. You could also just build in a tie-breaking metric. That's fine too, right? Yeah.
I mean, if you have your like nodes in a list or something like that, and you're cycling through them, isn't just the first one going
You
to
just take the first one.
like arbitrarily higher epsilon?
Yeah. So that's another way you could do it, right? You just arbitrarily break ties.
So I mean, on a test, would we have to explicitly write that, you know?
Oh, that you like
we
add a
choose the first
perturbation.
one in the list as the
I mean, you can say breaking ties arbitrarily. That's okay. Yeah. Yeah. Okay. Oh, another question? Yeah.
Is there like a priority of when you would use prims and when?
Yeah, they're equivalent. Yeah, I think cross schools is easier for me to understand, so I generally go with cross schools, but prims is fine too. Yeah. So on any like normal graph input, you would not get a minimum spanning forest out of cross schools. You would get a minimum spanning tree.
I think also like cross schools and prims, I think cross schools works better on sparse graphs.
Yeah.
And prims, but it doesn't matter because the runtime is the same. So you can just say you can use a minimum spanning tree algorithm on a test. You don't have to specify.
Yeah. To answer your question, each iteration of cross schools connects to unconnected connected components. Does that make some amount of sense? So connected component is just like a group, like a clustering of nodes that's connected, right? And so at each iteration of cross schools algorithm, you have a spanning forest, basically. And so that's how cross schools like produces a spanning forest at each iteration. But it does not necessarily mean that like at the end of the algorithm, once it's terminated, you'll have a forest. You will have a tree. right? And the only reason we maybe had a forest in the homework was because you disconnected that tree by removing that root node in your original input. That makes sense? Yeah. Yeah? So assuming all the edge weights are distinct, yes. If they're not distinct, then no. But like we just talked about, we can break ties arbitrarily and get an equally valid minimum spanning tree. Yeah. Yeah.
Talking about something distinct, and is what if we don't have distinct edges?
So again, the distinct edge costs, right? Yeah, so if they're not distinct, we can just break the ties arbitrarily. And the way that we specified how to do that was by perturbing each edge weight, or we can just, in a test environment, you would just say, just break them arbitrarily, choose whichever one, doesn't matter.
Well, what if we chose both edges? Would that create an issue?
If both edges would cause a cycle, then yes, that would create an issue, right? But otherwise, no. Yeah. Yeah?
Do we need to know how the runtime is selected?
How it's derived? No, you can just say that it's E log V.
Oh, but for like reverse delete algorithm, you're not allowed to slide this E log V
It's not
because
yeah.
it's fairly complicated.
But also just don't use reverse delete on your exam. Like there's absolutely no reason to, so yeah. Okay, so the proof of optimality for these algorithms, I feel like in your lecture notes was a bit skipped over, and they're really, really important. So like I strongly encourage you guys to review this stuff. But there are two really important properties that you need to know about minimum spanning trees, or that kind of underlie the correctness of minimum spanning trees. The first one is the cut property. The cut property says let S be a non-empty set of subset of nodes that's not equal to V, right? So just some strict subset of V, right? And let E equal VW be the minimum cost edge with one end in S and the other end in V minus S, okay? So in other words, the minimum cost edge that crosses the cut will be in every single minimum spanning tree of your graph, assuming we can have multiple, like we talked about. Okay, this is a super, super important theorem, like a super important property, right? I think they proved this property using an exchange argument in the book. So you should also go back and read that proof, kind of to give you another example of an exchange argument. But you have to have this property in order to prove the optimality of Kruskal's, right? Like what is Kruskal's doing at each iteration? Like it's connecting two distinct connected components. So it's taking the minimum cost edge that crosses the cut at each iteration and putting it in the minimum spanning tree. And with this property, we say that that edge must always be in every minimum spanning tree. So Kruskal's is indeed making the optimal solution. Right? So does this property make sense? I know the notation can be a bit weird, so I would say draw it out, right? And when we draw these things out, don't just draw the graph in the tree, like draw sets, right? Draw like some bubble S and some bubble V minus S, and then draw a bunch of edges going from S to V minus S, and like put weights on them, right? And denote that the minimum one is the one that's going to be in your minimum spanning tree. Yeah?
Like V here just means like the tree.
No, V is a set of nodes in your original graph. Like G, your input to the minimum spanning tree problem, is a set V and a set E of your vertices and your edges. Yeah? Sorry, can you speak up just a tad? Yeah. Yeah, so the cut property is used for like the optimality of Kruskal's, right? But like you specify that Kruskal's isn't supposed to create a cycle. And yeah, it wouldn't create a cycle because it's already in the cut, right? So that's another thing. Like, yeah, you don't need to reconnect two connected components that have already been connected. Yeah. Yeah?
Briefly repeat the question being asked.
Oh, sorry. Yeah. She said, so just to clarify, that means that like you can't create a cycle, right? The property doesn't create a cycle, right? But we're talking about a property, not like an algorithm, right? So like the cut property will not produce anything, right? Like it'll, yeah. But the algorithm will not create a cycle, and the cut property ensures part of that, why it won't create a cycle. Yeah. Yeah, here's the same kind of statement, just in fancier text. So feel free to go back and refer to it later. Okay, the second property that's super crucial for minimum spanning trees is called the cycle property, right? And I think this one is more intuitive than the cut property, but you still need to make sure you understand it well. So it's assuming that all edge costs are distinct. Let C be some cycle in your graph, and let the edge E equal to VW, be the most expensive edge in that cycle, C. Then E cannot belong to any minimum spanning tree of your original graph, right? So if I have just some arbitrary graph, I can immediately start getting rid of edges, like without running any of these algorithms, I can discard some edges as candidates for being in my minimum spanning tree by looking for the cycles, taking the maximum cost edge in that cycle and just removing it, right? And this algorithm or this property kind of underlies what the reverse delete algorithm does. It goes through all the cycles in the graph, it finds the maximum cost edge in the cycle, and it just removes it. And then if you keep doing this, you will eventually have a minimum spanning tree. Okay, does this property make sense? Okay, cool. Now we have an example. We want to find an MST using Kruskal's or Prim's algorithm. Here, I don't think we have completely distinct edge weights, so that should not really matter. But yeah, spend a couple minutes just drawing through it. And this might seem like a tedious exercise, like you might have this down, and that's great. That means you've done the studying. For those of you who haven't yet, done this little exercise, like make sure you can do this. This is important. So.
Use prints. It makes sense though. It's like
Oh no, not that one. That makes us like
I think depending on your route node, because you have edges with like similar costs. With the same cost, you lock in. This is a graph.
Oh no, I know. I was asking what I was. How do you get it? Oh, I showed you the Oh wait, no, you just have. Yeah, you just have that you go to B. That you had to go to C. Right? Yeah, but then you minimum like there's some different No, but you okay, you asked B, right? How to do that? Yeah, you want to make that yeah. And there's only one way to go. Right. But like that's so good. Yeah, how do you create the next one? I don't know, rationalize like even right, so even though we're at C, right, C is the only node that's not in our graph.
All right, so hopefully this problem was fairly simple. But if you ran Kruskal's algorithm, this should have been the solution that you got. So you would have just take df, gh, right? You would take the two edges of cost 1, you take the edge of cost 2, you take the edge of cost 3, and cost 4. You can't take this edge because it would form a cycle, and it doesn't really help because you've already spanned everything in your tree. Then you take the two 5s and the 6, and then you're done, right? So I like Kruskal's. I think it's the simplest to run, but you could also use prims and maybe QS. Oh, there's a second solution for Kruskal's. Oh yeah, it just takes the other edge. Yeah. And then if you use prim, so they started with root node E and extended out from that way. And so hopefully you got a solution that looks like that. And then they made a separate decision also starting from E and got the same other tree. Okay, this question is slightly more interesting, and I'll come around and answer you individually as people work on this question. But basically, we have a weighted undirected graph G and a minimum weight spanning tree T, and the graph G has n vertices and m edges. So suppose that we add a new edge to the graph, and this G naught is basically the new graph with this extra edge added in it, right? So it's E plus this new edge. Design an algorithm in O of n time to compute a minimum weight spanning tree T naught of the original graph. So what you cannot do is just rerun Kruskal's or prims. You have to do a little bit of thinking as to how to get a linear time algorithm that computes a minimum spanning tree of this new graph given the minimum spanning tree of the old graph. Okay, so I'll give you like 2-3 minutes or maybe 4 minutes to think about that.
Because you have to wear it. Wait, why is there?
It's the new edge.
Oh yeah, I didn't understand. It wasn't already there. You guys did.
I don't know exactly. I was like, I haven't read this.
All right, so I gave you guys a little less time for that one because I would like to give you guys enough time to take a break and then get on to DP. But the fundamental question here is, how are we disrupting the tree T if we add the new edge to that tree? Does anyone have like a good answer to this question? Yeah? Right, we necessarily induce a cycle in the graph because we didn't add any new nodes, we added a new edge, right? So if we add this new edge to T, there must now be a cycle, and we know where that cycle is in the graph because the new edge we added induced it. So then we just trace that cycle, find the maximum cost edge, and remove it, right? And that gives us a correct minimum spanning tree in O of n time. So is everyone kind of clear on that solution? It's simple, but there's some subtleties, yeah? We know the edge that caused the cycle, right? We know which edge caused the cycle.
Yeah, but how do you find it? Because the input gives you the edges as I don't know how it gives it a tuple maybe, but then how do you know which of them are the ones that created?
Yeah, we'll start from VW created the cycle, right?
Yeah,
It must have created the cycle. So start from VW and trace all the edges connected to it.
yeah, but the data given to us doesn't have like the vertex and what the edges are connected to them. It gives you the data of the edges.
You do BFS, right?
Yeah,
So you know how you like
you can just BFS
you
on the.
need to specify how you find it in the algorithm. Like that's the question.
Not really. I think that that specific implementation detail is a little lower level than what you need to do here. Yeah, but it's not super complicated to find the cycle because you know the edge that causes
We're
cycle.
just very
right?
surprised that the solution only has very short answers and not really discussing the details.
The exact details. I mean, there are some details that are more important than others, right? Yeah.
Can I do the proof on that one because like from the answer key, I don't really know.
A proof of this. Was this in your practice set or something? Oh, I didn't even look at your practice set. My bad. Yeah. Then yeah. How about this? We're gonna take a 5-minute break because that'll give us about 45 minutes to do DT. And then if you have like specific questions, you can come up to me without causing any hazards. Yeah. So cool. Take a break.
So I guess like the properties. Yeah, so what's the point of every not be in any means well, because now I have a cycle on my graph. I still need to have all the edges connected, right?
I think it's like cardio below its
I'm gonna be in every single episode.
Yeah, I know. You're already
Right there. I only know you see it every time we You started calling me Yeah, I'm like, it makes sense. It's so like
Oh wait, that's hilarious. Oh yeah.
Never say otherwise. Way to confuse. Stop murdering the kids.
All right, so DP is a pretty big topic and we have a lot to cover, so let's try and get settled down and go through it. Okay, how many of you guys struggle with dynamic programming in general? Just a good, okay, lots of people, yay. Yeah, it can be a kind of like unintuitive concept to grasp. I promise it's really not that scary once you get the basic intuition, but basically, actually, yeah, I'll kind of expand on that a little bit more. Like the way that this course teaches DP is not really my favorite thing. I don't know. I think they use a lot of extra words to describe a very simple concept, right? All you're doing is you're taking the most brute force recursive algorithm. So you're just going to explore like all the possible solutions that you can. And you're going to take the best one, and that's an exponential time algorithm. But then all we're going to do is just cache our solutions in the meantime, and we somehow get from exponential to polynomial. That's it. Right? So if you kind of like understand the intuition of memoization, then you understand why DP works, right? So we can go through a lot of examples, but the key idea is let's break a problem down into subproblems. So basically just use recursion on the problem to solve it. And typically it's a constrained version of the original problem, right? So we're working on a smaller subproblem. And then we can solve larger and larger subproblems to eventually build up to the solution, right? So what's like a super simple like recursive algorithm that we already know that kind of like demonstrates this, right? Consider like factorial or like Fibonacci numbers, right? So Fibonacci numbers, we take the Fibonacci number, so let's say we have some recursive procedure and we call fib of n. And fib of n is going to call fib of n minus 1 and n minus 2, and n minus 1 will call n minus 3 and n minus 4, and n minus 2 and n minus 3, and et cetera, right? And so if I call fib of 6, I get some recursive tree that calls fib of 5, fib of 4, and the fib of 5 will call fib of 4, fib of 3, and the fib of 4 will call fib of 3, fib of 2. People kind of follow what I'm saying, or am I saying fib too much? All right, but the idea is that if we just call that recursive algorithm, we have an exponential time algorithm, right? Because we have basically a tree of recursive calls, and we have a lot of repeated work being done. But what if the first time I call fib of 4, I just cache that solution, right? I say, okay, next time I see fib of 4, I just look it up in a dictionary, right? Or a map, or a array. And then I just search for fib of 4 before I actually recompute the answer from scratch, and boom, now I only have a linear sequence of calls. I don't have an exponential number of calls, right? So that's basic intuition. And that's what we call top-down dynamic programming, right? When we basically take the recursive solution, we just memorize the answers in some table and refer to it as needed. And then when we look at this top-down structure, we observe that the tree then becomes like this linear kind of graph structure. And I can just iterate from the leaf to the root instead of iterating from the root to the leaf, right? And so that gives us rise to this iterative approach to solving dynamic programming problems, which we call the bottom-up approach to solving dynamic programming problems. And this is the one that you see in most of the lectures because it tends to be easier to formulate. It tends to be a little bit easier to just like write down the iterative algorithm in a lecture setting. But really the intuition is the same. Like there's no difference between a top-down and a bottom-up solution other than the bottom-up solution is just kind of like filling in a table iteratively, right? Okay, did that make some sense? Yeah.
Wait, sorry, can you just top down versus bottom up? Is top down bad because it like
It's not bad.
blows the tree out?
Well, so if you do top down and you don't memoize, right? So if you do top down and you memoize your solution, that means like the first time I see fib of 5, I compute it and I put it in some dictionary. Then the next time I see fib of 5 being called, I can just look it up in the dictionary, right?
They're doing the same thing, just
Yeah.
kind of different.
Different order, basically, right? Yeah.
But that's what you call fib of 5, so you need fib of 3 and fib of 4, right?
Right.
But you don't have those memorized because you
Yeah.
haven't computed them yet.
So then it'll call fib of 3 and fib of 4, and eventually those will get computed, and then it'll get memoized.
Okay.
The bottom up approach, like
Yes. Yes, it can be wasteful, right? Because now sometimes like you don't need every entry in the table, right? And you compute them anyways. But it's easier to analyze runtime for bottom up, and so we tend to just, it's fine, right?
Wait, could you repeat bottom up, top down again? It's like
The bottom up being like, we're just starting from the bottom of the tree that we've constructed, right? And then top down we start from the top, right? So like in top down we say fib of n, right? In bottom up we say let's compute fib of 0 and fib of 1 first, and then let's compute fib of 2, fib of 3, fib of 4, all the way up to fib of n. Yeah. That actually, I encourage you, if you're shaky on the fundamentals of DP and you somehow like got handheld through the programming assignment, right? Just implement Fibonacci in all 3 ways. And that kind of builds a little bit more intuition for how to do this. Yeah. Also, it's not a bad thing if you got handheld on the programming assignment. Like it's fine. Like that's what we're here for. But yeah.
In the prelim, like which approach do we use? Like, is there?
Doesn't matter. We don't really care as long as it's correct. So
If we use like the top-down approach, then we don't really have to prove that we never access a part of the array that hasn't been filled, right? Like,
yeah, that's true.
so
yeah.
It would just be easier. Like it's like one less step in the proof.
Yeah, but then it's a little bit more complex to reason about the runtime of top-down approach because you're like reasoning about stack calls and not like loop iterations, right? Can you speak a little louder?
The recursive relation will be the same.
The recurrence relation would be exactly the same. Yeah.
You don't care about this call stack that it creates, like the additional space that.
Well, it does create a call stack, right? And it does cost some time and some space to do it. So you should analyze that in your running time.
But it's fine that it has additional space complexity now.
Yeah, that's fine. I mean, because you have space complexity in your table too. If you do bottom up, right? And I need to allocate an n by m array as an optimization, like an opt table, right? That introduces space complexity in the same way that a call stack would introduce space complexity, right?
But how does the top down without recursion?
How would it involve recursion, or how would you not?
How you not do it? You haven't start with an optimization. Right?
Top down is recursion.
Oh.
Yeah.
So you can't remember it.
Memoization is a part of recursion, right? Like I can do both.
But let's say you do 6 with 5, like I'll take this 3 and 6 with 4.
Should I draw this out on the chalkboard?
Yeah, they.
Okay. So yeah, I cannot draw this out on top load, right? But what Kira was just saying is that bottom up just means you start from the smallest subproblem, and top down just means you start from the biggest subproblem, right? So top down is inherently recursive, right? Because in order to compute fib of 6, I need to compute fib of 5 and fib of 4, and those are going to recursively go all the way down, right?
Yeah, so he's gonna be polynomial time.
It will still be polynomial time, because the whole point is that when I take the second branch of the tree, next time I need to look for like fib of 5, it's already been computed in one of the stack frames. That was called earlier.
But let's say you solve fib of 2, fib of 4, you don't have them computed, but you calling it on like a array or a data structure.
Yeah.
So what do you have there?
When he says top down, bottom up, top down is recursion, bottom up is DP.
Yeah.
So bottom up just means you're not starting from the biggest problem, you're starting from the tiniest subproblem and working up to the biggest subproblem, which is going to be like opt n comma L or something. Okay, and then top down is recursion, where you start from fib 5. In order to do that, you need to get fib whatever.
Right.
And you start and you break it down to subproblems until you get to the smallest one.
But the memoization comes in when like I've already computed fib of 5 on some branch, right?
Yeah.
So if I need to compute it again on another branch, I can just look it up.
Yeah.
So the first time I compute it, I put it in the table.
Okay.
And then some other process will then go and read it later. Yeah. Okay. So the way that we solve these problems, so you need all of these components in a dynamic programming solution to get full credit, right? So you need to specifically like explain what your subproblem is. This is a big shortcoming that people have on homeworks usually, because like if I don't clearly know your subproblem, then I don't know what your recurrence actually means, right? So you can't just write down a recurrence. You have to write down like what is opt of like k, right? What is the significance of opt of k? Once you do that, then you can specify what is your base case, what is your recurrence, and generally that fully specifies like a rough dynamic programming algorithm. And if you're going to go bottom up, then you need to kind of like draw the loops and specify what is the order in which you're computing across that table. And if you're going to go top down, you actually don't even really need to do that, right? Then optionally, some questions will ask you to actually recover like the sequence of decisions that led to the optimal answer. So that's the backtracing. And then you'll need a proof of correctness in the runtime analysis, right? And I will say, so in the past on like most algo exams, DP proofs of correctness are not particularly interesting. So, you know, it might not be required to like prove every algorithm on your exam. And in a good instance of that is usually DP, right? Okay. So in a little bit more detail, how do we kind of solve these problems? So we need to start by choosing the appropriate subproblem, right? So like the first sentence in your proof should be like, let opt of n be, and then in English, like what exactly opt of n means, or opt of I, or some variable that's less than what you're finally trying to compute at the end. And then you want to put in the characteristics that the problem actually has, and you want to claim that the original problem can be solved efficiently given the solution to the actual subproblem. So this naturally gives rise to like some kind of recurrence, right? And generally, so if you're asked to recover the optimal sequence of decisions, you don't start by trying to compute the sequence of decisions. You start by rephrasing it as like the numeric version of the problem, right? So rather than what is the subset of S with max value and total weight, what is just the max value? And then we can recover the subset by backtracing later. Okay. Yeah, so I guess here's an example using like the weighted interval scheduling. So the original problem is find the maximum total weight of a non-overlapping subset of the interval and of the intervals, right? So as opposed to the greedy interval scheduling problem, this one is asking us to basically maximize the weight because each interval has like some value. And the subproblem, opt of j, is the maximum total weight of a non-overlapping set of intervals out of the intervals going from 1 to j. So that should be specified in your DP problem, right? From there, then not only does that help us kind of like understand your reasoning, but that also helps you then come up with a recurrence. So opt of j can then be thought of as the max of, well, okay, if I take this interval, I can't take anything that overlaps with it. So it's the value of this one, and then the optimal value basically of the previous one that's non-overlapping. Or if I didn't take this interval, then I have the exact same solution that I had one interval ago. So it's opt of j minus 1. Right? So hopefully we remember weighted interval scheduling from lecture, and this kind of makes sense. And then we just use some answer to the subproblem to compute the actual optimal solution. So we just say opt of n, right? Because the optimal subset of intervals from 1 up to n gives us the value that we're looking for. Okay. So sometimes we need to go from one-dimensional optimization, or not really optimization, this isn't really optimization, like one-dimensional DP tables to two-dimensional DP tables or three-dimensional DP tables, right? And when can we kind of figure out when that is? It's when we don't have enough information in our subproblem to actually make a good decision as to what the optimal solution is, right? So in the knapsack problem, we wanted to find the max value of a subset of items with total weight up to W. And if we just try to encode the max value of items, we lose the constraint that it needs to be up to some weight limit W. And if we just try to like make some weight W, then we don't get the same like max value of items that we wanted, right? So we need both in our table, and we need to recur in both directions, basically. Yeah, so I guess here, like if there's some kind of capacity in the problem that's asking us to select, then adding that capacity into the table is usually a good first step. Also, sometimes like, adding another variable might not be necessary, but it doesn't make it incorrect, right? So if you're not sure if you should add an extra variable, or you're kind of like, oh, I think I might need one, like chances are just do it, and it will hopefully make it a little bit easier. I will say it will make your algorithm a bit more complicated. So you might have to do some more thinking about what the actual recurrence is. And then in the process of doing that thinking, you might realize that you don't actually need that second variable. Okay. Step 2, define your base case and your recurrences, right? So the same for like any recursive problem that you've ever done, you need to specify some kind of base case. And then you need to make sure that the base case doesn't depend on like anything else, right? Like it should be the smallest instance of your subproblem. And then the recurrence should follow kind of from what is the optimal decision that you're making. Oh yeah, go back. Yeah, so there can be multiple base cases, right? So if you have like a table that's two-dimensional, generally your base cases are along a row and along a column. And you need to think about what that actually means, right? So like, what if the weight is 0? Well, then I can't pick any items, can I, right? Or what if like the value is 0, or the item I'm considering is 0? Well, then I can't consider any items, right? So you should think about like what each kind of column and row in your matrix that you're building up represents.
I would also suggest for base cases not to just assume it's 0. I've been seeing that a lot, is just people saying like, okay, row 0 and column 0 is going to be 0. But if you're taking maximums or minimums, you might want to make it like a really, really small number like -infinity, or a really huge number like infinity, to make sure that they're actually choosing like the correct maximums or minimums. So just don't assume that the base case is always going to be 0.
Yeah, skip this slide. It's the same thing. So we've already seen. It's like the same ones from the book. Like they've seen these recurrences, right? Yeah. I guess so. Like, how do we decide what the recurrence is? So it's really easy if we're choosing between two things, right? Like, oh, do I take this or not? The decision's binary. Sometimes we need to loop over a set of options and then choose the best one out of all those options. And generally, like, this is why I don't think DP is that elegant, right? Because all we do is just iterate through all the possible options that we can make and choose the best. Like, that's why the proofs are also very uninteresting. I got a lot of questions in office hours like, oh, like, how do I prove this? Well, I mean, you're considering all the options. Of course it's correct, right? Like, you're going to take the best one out of everything. And so when you're creating your recurrence, just consider all the decisions you can make. Like, if you're placing a district, right, just consider all the places you can place a district and then take the best one. And that's your answer. I see blank faces. Some of you don't seem convinced. But does that make sense? Like, when you're constructing your recurrence, it's usually not that clever. Like, it's usually just like brute force, and it kind of is brute force, and then we're just adding some memoization, we're adding some caching to make it more efficient, right? Okay. No question. So, okay, so step 4, wait, can you go back to step? Yeah, okay, so how do we determine like the order in which to build up our subproblems? This is why I say like top down is usually like, I guess, easier to do this part, but then maybe harder to analyze the runtime, and bottom up is easier to do the runtime, but then a little harder to do this part. So in the top down approach, and then I'll talk about the iterative approach, the DP table is just filled with recursive calls, right? So, like naturally we'll only iterate over the options that it needs to make, and thus once we just store the results of all the table, we can just check if it's been stored already, if it's been computed already before making another recursive call. Right? So the ordering is kind of defined for us by when we call opt of n or opt of nl, it'll just automatically iterate through that tree and check if it's already been computed at each iteration. The iterative approach, we have this table, and so usually we just iterate over the entries of our table and fill them up using our recurrence, but you have to be careful that you're not going to be filling up entries that are like invalid, or that you're filling up entries and then ordering such that your base cases have actually already been computed into the table and you can refer to them when you're, iteratively building up your table, right? So if your base cases are like the first column in the top row, right, then obviously you can't just iterate like from the bottom left to the bottom right because you'll have things that haven't been computed, right? So you need to like carefully consider like what are your base cases, how do they relate to the recurrence that you've constructed, and then you can naturally then fill in the rest of the table to find the answer you're looking for. Okay, so this part is like the back tracing, right? So like how do you get the answer to the original problem using the answer to the subproblems? Oh no, this is not back tracing. That is not what it is. This is just saying, okay, I have the recurrence computed, I filled in the table, how do I actually find like the numeric answer to the problem? Generally, it's just the last thing that was computed in the table, but it might not be, right? There might be instances where you actually have to like iterate through your entire table and figure out which one had the max value. That's fine too. Just use the answers in your table and then figure out exactly what it is that you need from your table. All the information should be there, right? Yeah. And then finally, if we have a selection problem, which we rewrote as a numeric problem, we can then iterate through our table backwards, like I mentioned. And we'll show this explicit example of backtracing in one of the problems that we're going to do. But then iterating through that table, we can just recover the sequence of decisions that we made to get to the optimal answer, and thus recover the exact path that we need to return. Okay. So the proof of correctness in DP algorithms, again, you need to specify that like your recurrence is correct, and then you're filling in your table correctly, right? So usually, again, your recurrence is correct because you considered all the cases, right? Like this is usually a direct proof, and it uses some casework. Like, oh, obviously, I considered every place to cut the chocolate bar. Oh, you guys haven't done chocolate bar. Okay. There used to be a chocolate bar problem that was always given as a programming assignment, and we had to figure out like the optimal places to cut the chocolate bar such that like no square had both peanuts and hazelnuts or some shit like that, right? So like we considered every place to cut the chocolate bar, so obviously we took the maximal cut, right? So the proof of the recurrence correctness is pretty easy, I think. And then the inductive step is like, well, our recurrence was correct. So if the solution to my subproblem was correct and my recurrence is correct, then the solution to my next problem is correct as well. That's also like fairly simple, right? It like doesn't actually have that much rigor involved in that proof. Yeah. So like a lot of people are like, oh, like this proof seems like rather trivial. Like, yeah, that's the point. Like the hard part of DP is not the proof, it is the formulation, right? And then the runtime analysis should be pretty simple if you use bottom up. And if you're using top down, think about what it would have been bottom up, and then see if you can relate loop iterations to stack frames, and it should be roughly the same. Again, sometimes you'll get different runtimes, and you need to think carefully about what you'll do that the bottom up version didn't if you use top down. But generally, they're pretty close. So, yeah. Okay, so someone asked, oh, go ahead.
How do we prove backtracking?
I don't think you need to formally prove backtracking in like any case. So the question was, how do you prove backtracking? I mean, like assuming your table's correct, it is relatively trivial to just iterate through the decisions you made and recover the solution. Okay, not trivial as in like it's trivial to do, but it's like there's not a lot of ambiguity in like how you do that, right? Yeah.
So can we just say like use backtracing, or do we have to like come up with some data structure too?
So you should specify the way in which you do backtracing. It doesn't need to be as implementation heavy as like, oh, I'm going to store the information in a heap and then like go that way, right? But it should say, I traverse my table from opt of n, and I consider which decision was made, and then I get to opt of n minus 1, or I get to opt of n minus pj, whatever that was. Yeah. Yeah.
Like in cases that's kind of like come up with current relations, because like for example in like the RNA there was like the two when like J was fit or not, and like
yeah. So we'll go through a practice problem that will hopefully make it a little bit more clear, and I'll say some more at the end. Yeah, so how do we know when it's greedy or dynamic programming, right? So first thing I'll say is that any greedy algorithm can be solved with dynamic programming. So if you're really unsure, just use DP. That is perfectly fine. Don't do what I did. On my first exam, when I took this class, I swapped the two and lost like so many points. So that was rough. But I'm still a TA, so that's cool. And so greedy algorithms basically like there aren't many problems that greedy algorithms give nice solutions to, so which is why I say naturally your intuition should go to DP. But generally, if there's like a simple heuristic that you can make at every single iteration that you think will provide an optimal solution, that's when you make a greedy algorithm, right? DP is usually when your decision cannot just be locally optimal, but there are like globally optimal things that you have to look for that locally optimal conditions will not contain, right? So in the knapsack problem, it's like, what if I take some item at iteration I based on the fact that it has maximal value, but that prevents me from taking some item at iteration I plus 1 that would further optimize my maximal value over the entire interval, right? Those are the questions you should be thinking to yourself. There's also a question you should be thinking to yourself when you're proving greedy algorithms in general. Like, how do I know it's not the case that the decision I'm making now is preventing me from making a decision later down the road that would further optimize my solution, right? And if the answer is, well, there's nothing preventing that from happening, then it's probably a DP problem. And if the answer is, well, obviously I'm always going to make the best decision, then it's probably a greedy problem. So start with greedy, right? Like if it seems like a simple enough problem, start with greedy, try to come up with a few rules. But if you like find counterexamples fairly quickly to all your greedy algorithms, then just go straight to DP. Yeah, also I will, yeah, go ahead.
If you use DP for a greedy algorithm, are
Yeah.
you gonna get the same runtime, or can you get the same runtime?
It'd probably be slower. Yeah, probably slower. But that's fine, because polynomial in this class is considered efficient, right? I will say, so like generally the structure of these exams are you have like a couple algorithmic design questions and then a bunch of short answer questions. And so of the couple algorithmic design questions, I almost guarantee you it will not be 2 greedy questions, right? So if if you write 2 greedy algorithms on your exam, you probably did something wrong. Go back to check. Okay, yeah?
Let's say the runtime doesn't match the optimal, but
Yeah.
still polynomial, we still get both ways.
That's fine. Yeah, polynomial is considered efficient in this class. Like you aren't required to achieve the tightest runtime. Yeah?
Just write DP.
You could, in theory. Now it tends to be harder to think about, right? But you could. Yeah. Okay, let's move on because we're running out of time. Oh, okay. Here's a sample problem. So James is going to walk us through a sample problem.
Hello? Can you hear me? Higher? I'll just hold it. Okay, so for this one, we have 2 machines and we want to schedule them to run so that you can get the maximum value. If you schedule a machine at A at minute 1, you get 10 points, for example. And if you schedule machine B at minute 2, you get 1 point. But the problem is that if you want to switch the machine in the meantime, you will have to waste a minute. So for example, if you take A at the first minute and then you suddenly decide to switch to B, you have to like not do anything during the second minute. So the problem is how to find the largest value that you can get from scheduling the machine. So I'll give you some time to think about this.
So I showed you the reduction, but like try to come up with a recurrence. I don't think it's that difficult. A hint also is that often like you can solve these problems using one table, like one table. You could also construct two, which would make it like easier for you to reason about the decision that each one can make. So you have like opt A, opt B, right? Where you define your optimal subproblem, and then on A. And that's optimal solution ending on B, one on one. Or you can include it in one. I told them already.
For the office, why don't you use 1 minute?
But yeah, you can see too many details of like
How do you the current or is that just the algorithm?
There are some versions. The proof of your recurrence follows directly from the cases your recurrence.
Yeah.
Right, so like each recurrence will probably going to get all multiple decisions.
Yeah.
It's just going to take the best.
And that, is that the same thing you do? What? Is that the same thing you do? Like to what you give you?
Based on the fact that your recurrence is correct, you end up from small problems to bigger problems.
Okay.
But the proof of the proof of induction relies on your first-name factor. Yes.
So you have to design the recurrence, you have to complete
The proof of the recurrence is correct, and then you can read it really I also have an SD card. And then you have one for A and one for B.
Okay, so we don't have much time left, so let's go over it. So one of the ideas that you could have, the first idea could be that opt of I would just be the maximum amount of value that you can get from the first I time steps. But there's a problem with that. So the problem is that you don't know whether your maximal value comes from running A or running B in the previous time step. So that is not good. But the second idea is that we include which machine that we ran to get the maximum value. So for example, opt of 1 may be like the maximum value together with A or B. But the problem is that this would still be hard to keep track of, because sometimes you may need to use like the result that you get from a previous time step that's not really optimal. So for example, you could get machine B on the second time step that is not as good as machine A on the second time step, but on like a future time step, you need to refer to the one that is like less optimal, because it will actually become more optimal. So the final solution that we use is to have 2 DP arrays or a 2D array, depending on how you think about it. So you have opt of A and opt of BI. So opt of AI is the maximum value that you can get from 1 to I, provided that machine A is used at time I. And opt of BI is when machine B is used as time I to the maximum value. So can anyone come up with the recurrence?
Did anyone actually do this while they were solving the problem? Create 2 opt tables?
Yeah.
Opt AI equals like AI plus max opt AI minus 1 opt B I minus 2.
Yeah, that is correct. So first of all, we have the base cases where if you like go from time 0, then of course you cannot do anything. So your optimal value would just be 0. And if you go for time step 1, then if you use your machine A last, which means that you use machine A at time step 1, then you get A1. And if you use B, then you get B1. And the recurrence is dependent on how the problem was phrased. So if you look at the opt of A at time step I, it could come from A in the previous time step or B from the previous 2 time steps, because you have to wait a time step for B to come to switch to A. So it would be the maximum of opt of A I minus 1 and opt of B I minus 2, and vice versa for opt of B. And then the maximum value that you can get for time step I in the end would just be the maximum of these 2. So that would just be the recurrence. Next. And to build up this subproblem, you should notice that opt of I, whether it's A or B, only depends on the previous values I minus 1 and I minus 2. So you could first set your base cases, and then you just use the recurrence to compute from 2 onwards. So this is how you would write the algorithm, or at least this is the pseudocode. Anyone has questions about this? Yeah.
1D arrays, or like why can't it just be OPT of I comma A slash B?
Yeah, that is equivalent. So you could think of it as 2 1D arrays or a 2D array where the second one is just Boolean.
You could have like 2 columns, right? And the same number of rows. That's the same thing as just having 2 1D arrays, right?
Okay. Any other question? Yeah. What's your question? Oh, so we're returning the opt of. Wait, go back.
Doesn't say.
Yeah. Oh, so yeah. Well, the question actually asked for the schedule, but right now we're only computing the maximum value, and to get the actual schedule, we actually need backtracking, which let's see how we do that. So we know that, so for this example, opt of B4 turned out to be the larger value. So we know that this came from either opt of A2 or opt of B3 from the recurrence. So since there's only 2 choices, you can look at each of them. So which one of them will give you the maximum value? And you look at this step. If it's from 11, then so you know that B of 4 is 20. So the previous one, in order to get a maximum value, you have to have 30 in your opt, and that can only come from opt B of 3. So if both of them can give you 30, then you can choose either of them. It should be both should give you the correct value. And after you choose opt of B3, you look at which one of opt of A1 or opt of B2 will give you that value. So in this case, it turns out to be opt of A1, and then you just backtrack all the way to the back, and you get to 0. So that will give you the schedule. Alternatively, you could use a back pointer, which is next slide. So using a back pointer, you need to store which one that you're coming from in your table, or you could like start a new table of the back pointers, and then you just look up the back pointers as you go back. So that's also a way. So it's kind of a trade-off between so this checkup will just be O of 1 time complexity, but you need an additional memory to store it. So it's kind of a trade-off between memory and time. And this problem, you can backtrack either way and they give you the same asymptotic runtime because there's only 2 options. But if it's like a max, then it would be better off if you just store the pointer that you actually get the maximum value. So it'll be O of 1 for each step when you backtrack, rather than you have to go through all the values again to find the maximum. Question?
If we have to use backtracking on the exam for something, how in depth like do you have to get about explaining it or proving it?
I think you can just say that you're going to store the back pointer, for example. You can just say that while you're looking at the maximum, you also store the argmax, which is the actual place that you the actual number that you chose to get the maximum value. So it's not that complicated.
Kind of along that same vein, when you guys are writing your algorithms, you don't need to be super specific implementation wise. So you don't need to say like use, I mean, in this case, you might want to say specify that you're using a 2D array or something like that. But in general, when writing algorithms, you don't need to talk about like the data structures you're going to use and every single step. You could just say like, oh, get the maximum of this. You don't have to specify how you're doing it. And it's kind of the same thing with backtracking. You're not going to say, we're going to use like pointers and we're going to use like data structures to do it. You just need to specify at a high level what you're going to do, which is keeping track of it or going backwards from your optimal solution.
Question?
Space constraints don't really matter in this class. Should we just always use pointers?
Yeah, sure. You can also use that. Other questions? Yeah. Okay. So yeah. Are you going to?
Okay, so an alternative solution to this problem is actually reducing the shortest path. And I want to talk about this briefly just because it is a very elegant way to solve many DP problems. And what I mean by that is like, you don't actually need to understand what the hell is going on with dynamic programming to reduce something to shortest path and just say Bellman-Ford will solve it for me. So I do think it is, you have to be careful. It's not like going to apply to every single problem that you see. But in the vast majority of exam problems, I found that it applies quite frequently. So basically, the idea is we're reducing, right? So how can we use Bellman-Ford, which we know is a proven correct algorithm, to solve this dynamic programming problem? And so in order to create an instance of Bellman-Ford, we need a graph with directed edges and weights on all of those edges, right? And so what we're going to do is we're going to map every single minute or every single time interval I to a distinct node for each machine. So we're going to have 2 nodes per minute. And we're just going to have an arbitrary source and an arbitrary sink that kind of directs the path from S to T that we're looking for. And then we just run Bellman-Ford and we find that shortest path. And that shortest path will give us the maximal schedule. And the key nuance here is that we have to make the edge weights negative because we want to find the maximum objective. And so the maximum negative is going to be the same as the minimum that Bellman-Ford is going to return to us. And so I realize this is a rather brief description. So let's go ahead and look at the actual transformation of the problem, right? We're given this table as an input. And so when we're doing reductions, remember, we need to have some transformation that takes us from the input of the original problem to the input to Bellman-Ford. And the input to Bellman-Ford is a graph, right? With all these directed edges and these weights. So I introduce an arbitrary source and an arbitrary sink. And then I can add the nodes for every single minute and machine, right? So A1, A2, A3, A4, B1, B2, B3, B4. And the weight on the edge is the negative of basically the value I get by choosing that machine at that time, right? So from time 0, if I choose to start with machine A, then I get a benefit of 10 or a value of 10. And so the edge has a weight of negative 10, right? And I find that when I find the shortest cost path from S to T on this graph, I end up with the same optimal value that I would get from the optimal schedule, yeah?
Why is A1 mapped to B3 instead of B2?
Because every time you switch machines, you pay a cost of 1, right?
But shouldn't it, like, if like A1 switched to B2 in the next one, like wouldn't it like
You can't switch from A1 to B2. Like you have to go from A1 to B3, right? Because you pay a cost of not being able to run anything on the next minute when you switch machines in the problem statement. That's also important. You need to encode the problem restraints in the edges, right? Like you can't make edges from nodes that have invalid sequences of decisions or your reduction breaks down. Okay. And then also just note here, sorry, back in the picture, A4 and B4 to T have weight 0. And that just kind of represents that we need some kind of terminal state. And so that terminal state is represented by that node T, and there's no cost of like getting to that terminal state. Okay, and so the proof of correctness relies on the fact that there's a 1-to-1 correspondence between ST paths in that graph that we drew and schedules of machines from time I up to N, or time 1 up to N, right? And so here is the proof. I will post these slides online and we can talk a bit more about it. Yeah, brief question. No, Bellman-Ford is on directed graphs. It's not on non-directed graphs. It's only on directed graphs, actually, yeah. Okay, so it is 4 o'clock. I will let you guys go. But yeah, great work, guys.